Hello, welcome to another module in this massive open online course. So, we are looking at optimization for cooperative communication, alright, and in this module we are going to get to the optimization problem, alright. So, we are looking at optimization for your cooperative communication system. And well, what we have is we have a source, we have the relay, and we have a destination. So, this is my source, my relay and destination. We have also derived what is the expression for E given phi bar, that is probability of error at relay, error at destination given no error at the relay, that is phi is the event of error at relay, phi bar is the event of no error at relay, and this we can see is we have seen is 3 by 4 rho 1 rho 2 delta S d square delta R d square. We not explicitly derived this, but we said that this can be shown. Okay. So, phi bar implies no error at relay. Okay. And now probability of error. So, this implies, and now we already know the expression for the error at the destination. So, probability of error at the destination, we have seen this is probability of E given phi times probability of phi is and plus probability of E given phi bar. We said this is an approximation, but this is a good approximation which is tight at highest enough. Now, what we are going to do is we are going to substitute the expressions we have derived for each of these quantities and derive the probability of error at the destination. This is also known as the end to end error, that is the end is one of the ends is the source, the other end is the another end is the destination. So, this is the probability of the error at the destination, that is for the end to end communication, okay, because the communication happens in two phases, one is the source to destination, then source to relay, relay to destination. Okay. So, this is the probability of end to end error. This is the probability of end to end error, and now substitute each of these quantities. So, this is equal to, so first I am going to substitute probability of E given phi, that is error at destination given error at relay. So, this is 1 over 2 rho delta S d square times probability of error at relay, this is 1 over 2 rho 1 delta S r square plus probability of error given phi bar, this is 3 over 4 rho 1 rho 2 delta S d square delta R d square. Now, what is rho 1? Remember, rho 1 equals P 1 by sigma square, and what is P 1? P 1 equals power of source, rho 2 equals P 2 by sigma square, P 2 equals power of relay, alright. This is the transmit power of relay. And now what we want to do is, now we want to make an optimization problem where we want to minimize the bit error, the end to end error rate. Of course, we cannot just simply minimize it, because Minimizing the error rate simply means increasing the power infinitely, and of course, when the power becomes infinite, the bit error rate becomes 0. So, naturally that is not what we want to minimize this subject to a constraint, because the transmit power cannot increase infinitely. So, what we will impose is we will impose a power budget on this cooperative communication system. What is the power budget? The power budget is that the power of the source plus the power of the relay, this is a constant. So, this is a constraint which is a power budget for the system. So, this is a power budget which is a constraint for this cooperative wireless communication system. Now, P1 plus P2 equals P. Now, if you divide this by all sides by sigma square, we can get rho 1 plus rho 2 equals, well, P over sigma square equals rho equals P over sigma square. Further, to simplify this, because there are only two parameters, I can set rho 1 equals alpha times rho, rho 2 equals then becomes 1 minus alpha times rho, because rho 1 plus rho 2 should equal rho, where of course, because rho 1 comma rho 2 are greater than or equal to 0, this implies 0 less than or equal to alpha must be less than or equal to 1. Okay, this is now what is this alpha? You can think of this alpha as the power allocation factor. This is the power allocation factor which lies between 0 and 1, and rho 1 equals alpha times rho 2 equals 1 minus alpha times rho. Now, substituting these values, okay, substituting what are we substituting? Rho 1 equals alpha times rho, rho 2 equals 1 minus alpha times rho. And if we call this expression, if we call this as star, that is the probability of end to end error. So, substituting in star, what we get is the probability of error, probability of end to end error. This equals 1 over 4 alpha square rho square delta SD square delta SR square plus 1 over, or not 1 over, in fact this is 3 over 4 alpha into 1 minus alpha into rho square delta SD square delta RD square. And now, if you take this 1 over rho square common, or in fact I can take 1 over 4 rho square delta, or 4 rho square delta SD square, I can take this common into 1 over alpha square delta SR square plus 3 over alpha into 1 minus alpha into delta RD square. Now, if you look at this bit error rate expression, now if you pay attention to this bit error rate expression, you will notice something interesting. You will notice that the effective end to end bit error rate decreases as 1 over rho square. So, or the bit error rate at destination equal to 1 over SNR square. What is SNR? SNR equals P over sigma square. So, what you observe is normally in a wireless communication system, we have seen in the absence. Now, if you go back, okay, and if you go back and simply look at the source destination link, okay, I urge you to look at the source destination link. If you look at simply the source destination link, the probability of error decreases 1 over rho 1, it only decreases as 1 over SNR, alright. Therefore, this is known as diversity order 1, which is the exponent of the SNR is simply 1 in the bit error rate expression. However, so this is basically, you can say this is a 1 over SNR decrease, this decreases as 1 over SNR. However, now once you are adding a relay in this cooperative communication system, the bit error rate in cooperative communication system BR decreases as 1 over SNR square, and this is very important because the bit error rate is decreasing as 1 over square of SNR. So, the bit error rate decreases much faster. This is the impact of cooperative communication. Thus, cooperative communication leads to a significant decrease in the bit error rate of a wireless communication system, thereby improving the reliability. Okay. So, this implies BER of cooperative decreases this implies bit error rate of cooperative communication decreases significantly faster. This implies cooperative communication improves reliability, improves the reliability of a wireless system. So, this significantly improves the reliability of the wireless system. So, BR decreases significantly faster, because remember 1 over SNR versus 1 over SNR square for a cooperative communication system. So, this 2 implies diversity order equals 2. And this is also termed as cooperative diversity. So, cooperative diversity helps improve the reliability of a wireless communication system by making the bit error rate at the destination decrease significantly faster than it would have happened in the presence of only a source destination link, that is when the relay is absent. Okay, so, that is the important point to realize here. Okay. And now therefore, what we want to do, we want to find the optimal power factor alpha to minimize. Naturally what we want to minimize is, we want to minimize the bit error rate at the destination or probability of A. So, my optimization problem is now minimize probability of error. Okay. Remember, the constraint is now incorporated in alpha, because constraint was P1 plus P2 equal to P, which you have written in terms of alpha rho and 1 minus alpha rho, by writing P1 and P2 in terms of alpha and alpha rho and 1 minus alpha rho, or P rho 1 and rho 2 in terms of alpha rho and 1 minus alpha rho. Okay. And so, this is minimize probability of error, there has to be a dot minimize, which means minimize your earlier expression that we derived, 1 over 4 rho square delta SD square times 1 over alpha square delta SR square plus 3 over alpha into 1 minus alpha delta RD square. Now, observe that this is a constant, rho is fixed, P is fixed, rho is fixed, delta RD square, delta SD square is fixed. So, this implies this is a constant. So, we need to only minimize this part, which is therefore equivalent to minimization of 1 over alpha square delta SR square plus 3 over alpha into 1 minus alpha delta RD square. Let us call this as f of alpha. Df of alpha over d alpha, this is equal to minus 2 over alpha cube delta SR square plus or minus rather minus 3 1 minus 2 alpha by alpha square 1 minus alpha square delta RD square. Now equate to 0 to find the optimal value. This implies minus 2 1 minus alpha square delta RD square minus 3 into 1 minus 2 alpha alpha delta SR square equal to 0. This implies that 2 delta RD square minus 6 delta SR square into alpha square plus alpha 3 delta SR square minus 4 delta RD square plus 2 delta RD square equal to 0, and you can solve this. It is a simple quadratic equation, and what you will get is alpha star equal to delta SR square minus 4 by 3 delta RD square plus delta SR into square root of delta SR square plus 8 by 3 delta RD square 4 delta SR square minus 1 by 3 delta RD square, and this is basically your optimal. You can say this is alpha star equals optimal power allocation factor for minimum probability of error at destination. This implies that your rho star P1 star or your rho 1 star equals alpha star rho optimal power optimal SNR. So, this implies also that P1 star equals alpha star P. What is P1 star? Optimal source power. And this also implies rho 2 star equals 1 minus alpha star into rho implies P2 star equals 1 minus alpha star into P, and what is P2 star? This is equal to optimal relay power. So, that gives the optimal source relay power allocation. Okay, so, what we have obtained is optimal source relay power allocation. So, this is the optimization connect. So, optimization arises everywhere in signal processing and communication, what we are seeing is only a few salient and most relevant modern examples. Optimal source relay, power allocation for cooperative communication, which optimal in the sense that it minimizes the end-to-end bit error rate. Alright, so basically that completes our discussion on this cooperative communication system. We have a source, relay and destination nodes. Alright, and the relay employs the selective decode and forward, the SDF protocol, where it transmits only if it is able to decode the transmitted symbol correctly. Alright, and we have shown that because of cooperative diversity, the bit error rate decreases as 1 over SNR square, which implies that the bit error rate of cooperative communication is significantly lower, and therefore the reliability is significantly higher in comparison to that of having only a source destination link. This is cooperative diversity, and we have also derived the optimal source relay power allocation or power distribution. Thank you very much.